And we now have Zdenek talking about FPGA acceleration.
Once more, thanks to Jeremy for a very comprehensive talk about FPGAs, about the GPUs, because that makes me my contribution about FPGAs much more easier. So, hi. So I'm Zdenek from Maxfo Laboratory in Sweden. That's also a synchrotron laboratory, like DESI or accelerator laboratory. And how I got to the FPGAs instead of GPUs, it's like I was talking with a colleague of mine many years ago, who was a bioeducation physicist, is working at CERN before, and he was leading our Maxfo networks and infrastructure team. And I was saying, we are going to write a GRAN application, and we will, for processing data, which we have many, at synchrotrons and X-files, and we will be using GPUs. And he asked me if we are using FPGAs, and I replied that no, and say the very many good excuses why we don't do it, because we have also such amazing software, 5.5, and many other good softwares for CPUs and GPUs, but simultaneously I kept my mind open, and I was just thinking, okay, how one can do it actually, so later I was lucky because first of all our IT was open to order some, and then I met some FPGAs genius people like Kenneth Skovheed and Carl Johnson from a group of Professor Brian and Winter from Niels Bohr Institute, and we were discussing things like I was showing them, for example, the azimuthal integration that Jeremy was showing on GPUs, and they were able to implement it within few days on FPGAs and reach a data processing rate about 600 gigabits per second, like in some units. Let's say, and that's on that web pages. So I was saying, okay, there is definitely some potential. Plus we got funded. Here is just an overview and motivation of what type of data processing we usually do at photon sources is, and a motivation why this talk in the HDF5 hack, all X-ray data or X-ray scattering and imaging data acquired by Maxfo data acquisition are stored in HDF5 format, of course. And most of the 2D images from scattering experiments and are in bit shuffle as F4 compressed. So, that's important. Like why FPGAs? They are a typical real-time hardware. They are very parallel, and they have high performance and throughput. They have integrated networkings. That means that they couple well with detectors. They are very power effective. And as GPUs, they are a common existing hardware that exists here and has many applications in, I don't know, defense, telecommunications, medicine, medical instruments for medical applications. So they will exist. Even we will not be using them at synchrotrons for data analysis. The cons, people believe that they are difficult to program, which I do not think it's true anymore. They are difficult to install. I think that it's already also working. Mainly, there are other options how to use them. And they do not have still such a rich scientific software ecosystem, which I think is a little bit true, still. But even before our work, there exist many other applications. For example, Maxime Martelli developed many years ago already tomography reconstruction algorithms at FPGAs. Philip Leonarski has a data acquisition system for a Jungfrau detector, for serial crystallography applications. And recently, Cesar Gonzalez at the Barcelona Supercomputing Center developed algorithms for simulation of small angle and PDF curves. So, pair distribution function curves. So what are FPGAs? If anybody that is not does not know much about them. So there are arrays of logical gates. Yeah, like nowadays FPGAs, they have almost like millions of these gates. And these gates can be programmed by creating connections between logical blocks. That's illustrated on that picture in the right top corner. Yeah, they are arranged in functional blocks. Like there can be special blocks for example, doing floating point add and multiply. Yeah, multiply and add. There are special blocks for doing I/O and for communicating with memory. Yeah, their performance is high, comparable with GPUs, whose they can reach 10 teraflops today. And usually they are programmed in some special languages like Verilog, VHDL, that I am not using, by the way. Yeah, they are ideal for bit-level data manipulation. And okay, usually FPGA is just a chip like CPU, but you will get them on FPGA board. They will contain some network interfaces, PCI Express connection, often to your host computer, and some memories. Yeah, so it's very similar to GPU. This is why I'm showing also this example of comparing the parallelism at FPGA and GPU. The FPGAs are like a network of smart units, or these logical blocks. Then this means that each of these logical blocks has its fixed set function. Yeah, so for example, first block will load a pixel value 1. Yeah, in the next time step, it will send this value 1 to the another block, yeah, which will do a multiply. And meanwhile, the first one will also load the next value 2 and so on. So the third cell is doing add operation, like adding 1, for example, and the 1 is having output. Yes, so there is a typical pipelining. We see that with latency 4, we got a result, and it is absolutely clear that we will be getting a result every other clock cycle. So we have a processing throughput 1 pixel per clock. Yeah, on GPUs it will be very similar. There are multiple processors that will first load data, then they will multiply them, then they add, then they store. And so they will get 4 pixels at 4 clocks. Yeah, so the same processing throughput. So if they run on similar clock speed, they will likely have a very similar performance. With this slide, I wanted to illustrate when Jeremy was showing the timings for his OpenCL kernels or tasks. He was showing this in time. FPGA is really parallel hardware in that sense, that you can imagine it more like a factory where you have a lot of processing units, and you dedicate these processing units to special tasks. And all these tasks are running really in parallel. So this means that some piece of hardware is loading data, some piece is decompressing them at the same time when another one is azimuthally integrating them. Yeah. Yes. So when I am speaking about performance, it means that if I have a performance like 1 pixel per clock, and the clocks are running on 500 megahertz, then I see that I can process this number of pixels per clock per second. Yeah, and it means that really everything is happening in parallel, in that sense that if I look on, for example, an ancient mill, that is letting run a saw, then all the wheels are rotating at the same moment, and they are doing something. Yeah, how one can get FPGAs for people who are not from synchrotron facilities. At synchrotron facilities, we usually go into the medium size or large size FPGAs that are quite expensive, and they have very high network connectivity. They are running on more than 100 megahertz, usually 300, 400 megahertz. They can have quite reasonable power consumption, like 50, 100 watts. And they are also expensive, in almost it can cost, for example, $10,000. Like a really good FPGA or very large one. On the other side, there are also small FPGAs that are very power effective and really you can even afford them like a hobbyist. You can buy them in shops with electrical components and small like kits like PyNQ for ZinNQ you will get for $100. Yeah, and I would not underestimate them because they are very, thanks to their power effectivity, they are very good for example for applications in space. Yeah, and I am personally running in HDF5, like reading HDF5 and writing HDF5 data on a SoC, of that size. Yes, so even on such devices, one is running HDF5 library. So another option is to don't buy anything and just go on a service that is called Developer Cloud, provided by that company that is written there on GitHub. And you can just go there, apply for computing that you would like to develop something for FPGAs. You will likely be granted time. And you can try things like the project that we are presenting or develop your own projects there. Yeah, like motivation. When I'm speaking about FPGAs, I have, I think that here I do not need to speak much, but about this again. But the previous speaker was showing examples of, for example, a 4-megapixel detector, speaking many times about it, running on 1 kilohertz or 2 kilohertz frame rate, which the detectors nowadays definitely can do. Yeah, so they then they produce about 8 gigapixels per second, and this is the amount of pixels that needs to be processed. If the pixel has 2 bytes, these are then 16 gigabytes. Yeah, for me, actually, the question with FPGAs is, what does it mean fast? If it is low latency or high throughput, and I usually mean with that high throughput. Yeah, because I can also value fast reaction time. So, because the latency can actually depend on what I mean, processing latency of processing one image or latency of reacting on something. Yeah, what I would like to say that for curiosity is that at the nowadays CPU servers, like previous speaker was showing, for example, that server can definitely have a performance of 5 teraflops, or GPU can have 10 teraflops. Yeah, and we are speaking here about processing, for example, 2 or 4 gigapixels per second. Yeah, this means that there is a factor of 2,000. Yeah, between these values. So this means that we need about 2,000, like for processing our pixel, 1 pixel, like this server could process 2,000 floating points. Do 2,000 floating points operation, which is like amazing number if you compare what we just need to do often with data. For programming FPGAs, we are using high-level tools. Yeah, for example, my co-workers, they develop a synchronous message exchange and language. Yeah, I am personally using for this project OpenCL and SystemCL and one API. There are also other variants of C++ with pragmas, as I call it, that is high-level synthesis. For orchestration, one can use on the host. Yeah, one can use Python or C++. And for interacting with HDF5 format, I'm using libHDF5 and H5Py actually. Yeah, yes. So I am a fan of frameworks because frameworks can help, especially beginners, when they to accelerate productivity at the beginning of the projects. And the most famous frameworks for FPGAs are PyNQ, that is high-level synthesis is Python, OpenCL that I'm using, Open API, OpenCAPI, The advantages is that you don't have to write Linux Windows drivers, otherwise that you would need for FPGA. You don't need to use an extensive, extensive ecosystem that is around programming FPGAs, yeah, for electronics engineers. That's really very like its own field. Yeah, you can reprogram FPGAs very quickly. So, your FPGA can do, for example, serial crystallography application, and in 1 minute later it can switch to tychography application. Yeah, yeah, you have diagnostic utilities, and you have API for C++ or even Python. So at the end, I am doing exactly the same thing, very similar thing as the previous speaker. I'm usually reading with H5Pi, H5D. I'm using read direct chunk to read data. On CPU, I am optionally using bit shuffle decompress LZ4, and then I'm using PyOpenCL NQ copy, yeah, and PyOpenCL NQ and derange kernel. Yeah, yes. So it's a PyOpenCL together with Python and H5Pi. Yeah, and HDF direct chunk read is the key ingredient that allows this work. I am still doing for some applications decompression on CPU. Definitely now we are still doing decompression on CPU, but we are switching to decompressing on FPGA. And for this, the direct chunk read is the important thing for us to get the uncompressed data, still compressed data. Yeah, azimuthal integration. The previous speaker was describing it. It's a method of getting a pixel value into the powder pattern, or like scattering pattern. It's actually only histogramming or bin counting. It's nothing more. And you can describe by, you may do some corrections, like multiply the data in the image, or multiply data in the result 1D pattern. But actually, it's just bin counting with some multiplications, or you can describe it as a sparse matrix multiplication, where the sparse matrix is, for example, 10,000 by 1 million. Yeah, because one dimensions are pixels and one dimension is size of the 1D result. Yeah, in this way, you can also nicely split it, the physics and geometrical part, yeah, and do it on CPU, and you can do the high performance things on and high throughput on for example, compute accelerator, or you can do it with NumPy bin count and sparse matrix multiplication. Yeah, so we actually want to do bin counting or histogramming. I'm saying that's a relatively simple algorithm on FPGAs. So Karl from Johnson from Niels Bohr Institute was able to implement this in with synchronous message exchange in 1 day, but he did it this only for integers, like integer values. We didn't have the floating point corrections, but at that time he was able to immediately reach on a large FPGAs, these expensive ones, about processing rates about 20 gigapixels per second. Yeah, actually, when we are programming this with OpenCL, it is nothing more than a trick called Shannonization, which is well known, to just do it. So it's nothing really complicated. When one wants to extend integers to floating points, then I did it like that. It was necessary to reorder the results. So we were doing some BSORT and resort algorithms there. And this can be expressed in the like ways of systolic and the languages of systolic arrays, and that's actually all quite good. If something can be like understood like systolic arrays, then it can be well implemented on FPGAs naturally. Yeah, like a basic calculation shows that we should be able to reach 10 gigapixels per second. And if we look on what we manage on a medium and large FPGA, this is how is the algorithm running now. And it's visible that on medium FPGA we can process about almost 6 gigapixels per second. On large FPGAs, by just porting the thing from the medium to large, immediately we got to 9 gigapixels, likely because of increase in the frequency. So this is actually comparable with GPUs. With this slide, I'm usually illustrating that because we are using PyOpenCL and OpenCL, PyOpenCL, and Python. We are also having everything in notebooks. So the project that is describing this has a demo as a notebook, yeah, that runs in that developer cloud. Yes, so it's possible to try it. Yeah, and now I have only a few slides about decompression, which is still not finished. Yeah, but there is a progress in this large one because, as I was saying, I'm using OpenCL with the cards from Intel, and and recently I found that in one API examples, there is an example on decompression where there is a decompression pipeline, full decompression pipeline for gzip decompression and compression, and for snappy decompression. Yeah, the snappy decompression contains the LZ77 decoder that actually is dealing with the history buffer. It has also such options like multi-byte in and out, so it is very high performance. And so, because my project is in OpenCL, we retrofitting from one API took actually a few hours. These languages are almost same. The one API is, of course, much advanced. And what is necessary to replace is the snappy reader, which is interpreting the snappy like encoding of the data and producing the LZ77 instructions. Yeah, for the next part of the pipeline. Yes, so it's necessary to replace this thing and at the bit shuffle stage, which should be really natural on FPGAs. So for that, I have a comment, and there was already so over here it is actually like a scheme how looks the LZ4 sequence, and the problem of this sequence is that there is a 1-byte token. Then there are some bytes that can describe literals, how many literals there will be. Then there are literals themselves, and then there is offset and match length, which is again like unlimited length. So there are 3 fields that have unlimited length actually. Yeah, the match copy operations are mixed with literals partially. Yeah, so it's not easy to interpret on a parallel hardware this LZ4 sequence. It is actually easy, but only if you do it, for example, 1 byte by byte, or you are limited. With Snappy, it is possible from reading just 5 bytes ahead to now what is happening. Here it is not so simple. And this forced me that I implemented the whole thing actually also in Python to see how bad is the life without the proper libraries. And everything was extra slow. On the other side, it allowed me to extract some statistics. Yeah, so I could look into the compressed data, and for example, one could see that average what is the histogram of literal lenses in typical like Dectris Eiger 32-bit 16 megapixel from macromolecular crystallography experiment. Yeah, so I removed here the literal length of 1, yeah, because there is always a peak at 0, like at 1 or close to 0, yeah, and it is visible that there can be actually literal lenses. There are sequences that contains up to 600 literals. Yeah, that's interesting. And what is even more interesting, there are sequences that contains match lengths up to 8,000. Yeah, so but there are not many. That's the problem. Another thing is that at LZ4 is adding only to maximum 252 to each of these lenses, yeah, per 1 byte. So this actually means that our sequences in our compressed photon science data are relatively long. Yeah, the match length bytes can be about 30 bytes. Yeah. So this means the sequence is really long. Yeah. On the other side, one can look in opposite way and ask how many sequences are in total bytes at maximum in have 3 bytes, 5 bytes, 4 bytes. And it is visible that already 85% of entries or sequences have only 5 bytes. And for example, 33% have 3 bytes, and 3 bytes is a poor copy match operation in LZ4, LZ77 compression schemes. So this can be really, one can speculate on like a configurable hardware as FPGA is. So this means that I can use some of the hardware to say, okay, I will speculate that I have a sequence that is 3 bytes, 4 bytes, 5 bytes, and these things I will solve in 1 clock time, and this means that and it is visible that at approximately with this I will handle about 85% of sequences. So this is a summary. We can do azimuthal integration not only on GPUs but also on FPGAs with the standard scientific precision. I'm using usually float 32. Direct chunk read is extra good to get the uncompressed data. Having the compression on FPGAs is already very close. And I would like to help these people from Maxwell Laboratory and from Niels Bohr Institute in Copenhagen who helped me, and also some agencies for funding us. Thank you for your attention.
So thanks very much. Do we have any questions? Yep, back there.
Hello. One question. So with these FPGAs, you can process very fast, but I am curious, how do you transfer data from your computer to the FPGA without having some kind of bottleneck?
So this is a very good question. On FPGA, you can transfer data. As I indicated on the slide, I'm using like OpenCL NQA copy. So I do it by this will like transfer data over PCI Express bus. The FPGAs that I am using actually do not have a very high PCI Express bus bandwidth. The medium size has like 6 gigabytes per second, and the larger one has only 10 gigabytes per second. So this is a good reason why to decompress also on FPGA, because actually with FPGA I can process really a large amount of data, and likely I have troubles to deliver them to FPGA. Another reason why to decompress on FPGA is that because we can process so much data, we are creating also a high bandwidth requirement on internal memories on the FPGA board. And this is actually also a bottleneck. That's a bottleneck for the medium card. Then there is another way how to get at data on FPGA, because FPGA naturally have usually their own Ethernet interfaces. It is possible to deliver data to FPGA directly, for example, from a detector or from another FPGAs. Usually I would recommend some type of Ethernet, like Ethernet messaging protocol, for example, UDP. UDP protocol, datagrams. Not TCP/IP. That's not a good idea. But so you can deliver directly over Ethernet interfaces or over the PCI Express bus or some additional bus, like for example, in this OpenCAPI has its own connection between the processor and additional connection between the processor and the FPGA. And for example, now the new FPGAs are coming with a new standard that is called Compute Express Link. So there are even 3 ways. So
thank
that's
you.
Thank you.
Any other questions? Okay, I guess if not, then thanks again.